is being recorded.
Okay, all right. So welcome to this course. Today is the first lecture, and we are going to today do very preliminary things. We are not going to see a lot of difficult material right now. But what is this course about? So let me just start with what the Rogers-Ramanujan identities look like. So there are two Rogers-Ramanujan identities, and both of them were first written down by Rogers in 1894, and then rediscovered by Ramanujan in 1913, and finally proved by Ramanujan independently in 1917. So the rediscovery of the Rogers-Ramanujan identities by Ramanujan was quite good actually for Rogers, because he was not very well known earlier. But after Ramanujan's rediscovery, he became quite well known, and he was also elected as a fellow of the Royal Society. So what are these identities? And these are examples of Q series identities. Okay. So for us, Q in this course is always going to be some complex number, but not only that, we are going to take mod of Q less than 1. Okay. This is always going to be true. Whenever you see a Q appearing, mod of Q is always going to be less than 1. And because of this, I'm not going to write this repeatedly, that mod of Q is less than 1. So you please assume that mod of Q is less than 1. But we can also think of whatever I'm going to do as formal power series. So I'll explain what that means in a bit. Okay. So the first Rogers-Ramanujan identities, let's call it R1, is this. So the two identities on the left hand side, it's always a sum. Okay. And in the top, you have Q to the n square divided by 1 minus Q times 1 minus Q square, and so on up to 1 minus Q to the n. And the summation runs from n equal to 0 to infinity. And the second Rogers-Ramanujan identity is almost the same sum. So you still have everything Q to the n square divided by 1 minus Q times 1 minus Q square, and so on up to 1 minus Q to the n. But this time you also have a extra factor of Q to the n in the top. Okay. So you have Q to the n square plus n. So this is the right hand side of the left hand side of the first two Rogers-Ramanujan identities, and both of these left hand sides are an infinite sum. On the right hand side, you actually have an infinite product. Okay. So, and again, the products are almost very similar. So for the first Rogers-Ramanujan identity, you have something like this: 5k plus 4, and here k is going from 0 to infinity again. And the second Rogers-Ramanujan identity is now looking at the other residue classes mod 5. So if you look here, then you see that the first identity is looking at the residue, so it's looking at the residue class 1 mod 5, and this is looking at 4 mod 5. This time we're going to look at 2 mod 5 and 3 mod 5. Okay. So these are the two Rogers-Ramanujan identities. And the remarkable thing about these identities is that on the one side you have a sum, infinite sum, and on the other side you have an infinite product. So these are some of the very finest examples of such type of identities. Now several more identities of this type are known, and we're going to look at some of them towards the end of the course. But our main focus will be on trying to prove the Rogers-Ramanujan identities, see several different proof techniques, as well as give a combinatorial interpretation of both the sides of the Rogers-Ramanujan identities, and hopefully also give some idea of how to prove that combinatorial interpretation. Okay. So I forgot to mention, but if you have any questions, I think you can unmute yourself and just ask me whenever you feel like that. Okay. And if there is, any problem with the slides or voice or something, please just stop me.
Okay,
so
Professor,
yeah.
in R2, I mean, in the last line, 1 minus Q,
To the
5k plus 3 or 3.
5k plus 3. So this is 5k plus 3, and this is 5k plus 2.
Okay.
Okay. All right. So these are our main goal of the course, and these appear in several different contexts. So for sure they appear in number theory, they appear in analysis, they appear in combinatorics, they appear in the theory of integer partitions. They also appear in representation theory of Lie algebras. So we are going to see some of these applications. Again, everything is going to be self-contained. Even if you don't know in any of these things, then don't worry. So we are going to look at um, some of these things later on. Okay. So these are the first two Rogers. These are the two Rogers-Ramanujan identities. So in this course, we are going to deal quite frequently with integer partitions. I'm sure that almost everyone knows what are integer partitions, but still, for the sake of completeness, I'm going to define them properly, and I'm going to do little bit, so a very few, interesting results, first results of integer partitions. Okay. So what is an integer partition? This is just a way of writing any integer as sum of smaller integers. Okay. So in a partition of, let's call it lambda of n, and we also denote it by this symbol. So lambda is a partition of n, is a sequence of this type. So let's say lambda 1, lambda 2, and so on, up to some lambda k, where the sequence is non-increasing. So that means lambda 1 is always greater than equal to lambda 2, which is greater than equal to lambda 3, and so on, with, and this is important, lambda 1 plus lambda 2 up to lambda n is equal to, lambda k is equal to n. Okay. So this is the definition of an integer partition. Now, if you actually relax this condition that the lambdas are non-increasing, then you get what is called a composition of n. Okay. So you can, sort of take some permutation of the partition and get what is called a composition. So we're not going to deal with composition, but for us, we are going to be interested in integer partitions. So these lambda 1, lambda 2, and so on, these are called parts of the partition. And here k, which is the number of basically it's the number of parts, is sometimes denoted as L of lambda, which is also denoted by length of lambda. Okay. So this is just the number of parts in the partition lambda. And final notation is what is called a norm of lambda. So this is basically just the sum of what is lambda 1, lambda 2, and so on up to lambda k. And if lambda is a partition of n, this is going to be equal to n. Okay. So let's look at some examples. So we are always going to fix. Okay, one more thing I should mention is the notation that we are going to use. So we denote by P of n the number of partitions of n. Okay. And let's see the partitions concretely for some small values of n. Okay? So let's do up to n equal to 5. Okay. So what is, say n equal to 0, we can actually think of the unique partition of 0 to be the empty partition. So there is basically nothing. Okay. So it's just the empty partition. So that means P of 0 is equal to 1 for us. Okay. And it's also a convention that we'll apply. If n is equal to 1, then there is only one way to write 1 as a sum of integers, right? So this is just 1, and P of 1 is again equal to 1. If n is equal to 2, then we have two ways now. Now we can write 2 as just 2, or we can write it as 1 plus 1. So that means P of 2 is going to be 2. And if n is equal to 3, again by the same argument, we get 3. We can also write it as 2 plus 1, and we can also write it as 1 plus 1 plus 1. So P of 3 is equal to 3. And n equal to 4, we can write 4 as 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and finally 1 plus 1 plus 1 plus 1. So P of 4 is equal to 5. And I thought I'll do it, but I will not do it. So you can verify yourself that P of 5 is equal to 7. Okay. So these are the some small values of P of n, and P of n actually grows quite fast. So already if you calculate P of 200, it will be a very large number. Okay. And we'll see eventually, maybe today or the next lecture, how to get the values of P of n if we know some of the earlier values of, let's say, P of n minus 1, P of n minus 2, and so on. So we'll basically look at recurrence for partitions. So there actually different ways that you can visualize partitions. Since we are going to deal with some of the combinatorics in this course, so it's useful for us to look at some pictorial representation of partitions as well. And the one that I prefer is what is called the Farrer's diagram of a partition. So it's very easy to actually visualize. So if you look at a partition, so let's pick, some random partition of, I don't know. So let's say 7 plus 6 plus 5 plus 5 plus 3 plus 1. So this is going to be a partition of 27, I think, right? So this is, if you sum this up, it's going to be 27. So this is 7 plus 6, 13, plus 5 plus 5, 23, 26, 27. Okay, so this is a partition of 27. And we want to visualize this partition in some pictorial way. Okay, so the way that I prefer to do it, and which is also what is done in the textbook that I'm following, is by means of a Farrer's diagram. So what we do is, we look at the first part, which is 7 here. We just put 7 dots in a row. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, 7 dots in a row. We look at the second part, we see 6, and we put 6 dots in the second row, which is left justified. So that means the first dot has to be directly below the first dot of the first row, and we continue. So we put 6 dots, and we do this. For the third part, we see 5, we put 5 dots. The fourth part is also 5, we put 5 more dots in the fourth row. Then we see a 3, we put 3 dots in the fifth row, and then finally we have a 1, and we put a single 1 in the seventh row. Okay, so this is the pictorial representation of the partition that was mentioned here. Okay, and this is called the Farrer's diagram of the partition. You can also put boxes instead of dots. Then what you get is a Young diagram. So we will not do Young diagrams, but I'll just show it. It's very easy. Again, we just put boxes instead of dots. So in the first row, we put 7 boxes instead of 7 dots, and we'll just continue. So next will be 6 boxes. Then there will be 5 boxes 2 times, and then there will be 3 boxes, and finally there will be 1 box. Okay, so this would be the Young diagram of the same partition. So in certain context, we would like Young diagrams, but for us, this is enough, Farrer's diagram. Okay. So just remember that there is a pictorial way of dealing with partitions. But now this pictorial way actually gives us our first result. Okay. So if you look at this picture, then you can find out this result, which is, let's call it a theorem, which will be one of the easiest theorems that we'll prove today. Okay, so the number of partitions of n with n parts is equal to the number of partitions of n with largest part n. Okay. So how to see this, and the proof is going to be a picture. Okay, so if you let's take n equal to so let me just draw first. Okay, so let's say I have this, so which is going to be a partition of 11, n is equal to 11, and it has 4 parts, so m equal to 4. Okay, so now if you think about this, there is a nice axis along which we can reflect this. So if you look at the diagonal, which is drawn here in blue, and if you think of the reflection along the diagonal, then what I'm doing is basically I'm converting the columns into rows. So the first column had 4 dots. I'm just going to reflect it along that diagonal, blue diagonal, and make that column a row. Okay. The second column had 3 dots. I reflect it along the diagonal, and I make a row of 3 dots. The second row will be 3 dots. And I do this for all of the other columns. So the third column has 2 dots. I put in 2. The fourth column has 1 dot, and the fifth column has another dot. So what I did was I just reflected the partition along the diagonal. Okay, this was one reflection I got here. And if you think about this, if I do another reflection, then I'll go back to whatever was the first partition that I started with. Now the number of dots has not changed because I have just changed columns into rows. The dots have remained the same. So what I got here, the second partition, also is a partition of the same number, 11 in this case. Okay, but now if you think about this, the largest part, which is basically the first row, was the first column of the previous partition. Okay, so in that case, the first column signified the number of parts. In the first picture, the first column signified the number of parts, and in the second picture, the first column became the first row, which signified what is the largest part, and this was m equal to 4. So this is sort of like a proof without words of the result. Okay, so any partition with m parts can be, transformed into a partition where the largest part is n using this operation that we just did. So this operation has a name because it is very useful in many contexts, and this is called conjugation. Okay, so if you start with a partition lambda, then if you do the conjugation, which is just reflecting along the diagonal axis, you get what is called the conjugate partition, and it's usually denoted by lambda prime. Okay, so this is called the conjugate partition. Right. Okay. So this was quite an easy result if we think about this pictorially. There is also a proof without using pictures, and for that we'll need what is called the generating function, okay, of partitions, or of in general of any combinatorial object. So let me take a brief digression into what for me is a generating function, and what we'll focus on from now on. Okay. So if you think about any integer sequence, it need not be a sequence related to a combinatorial object. It can be any integer sequence. Okay. So if you have an integer sequence, let's say an, say n greater than equal to 0, then associated with this integer sequence, we can write a power series. Okay. So we can write a sort of infinite series, and that series is something like this. So a0 plus a1q plus a2q square plus a3q3 and so on. Okay, and in more shorthand notation, we get this n going from 0 to infinity, an q to the n. Okay, again, as I mentioned, whenever you see a q, you can assume that mod of q is less than 1, but now I'm going to tell you what is a formal power series for you. So this is an example of a generating function. This is the generating function of whatever this sequence we started out with. Okay, in particular, if we started out with the sequence of partitions, so that means we had p0, p1, p2, and so on. If this was our sequence, then the generating function would be just p of n q to the n equal to 0 to infinity. Okay, so this would be the generating function for partitions. You pick your favorite combinatorial object, or you pick your favorite combinatorial sequence, and you can associate that sequence with a generating function. So what do I mean by, I have used this word twice now, formal power series. What do I mean by this? So, I mean, there are several ways that people can think of this, but the way that I prefer is the following. So for me, anytime I see a generating function, or anytime I see, product of generating functions, or whatever, so Q products, which will come later on. So for me, every time some infinite series is coming up, I always think of it as an infinite degree polynomial. Okay, so this would be something like an infinite degree polynomial. And if I think of this in this way, then I don't really need to worry about convergence or divergence of that series. But in any case, convergence will be taken care of if we just take mod q less than 1. But I don't want to repeat mod q less than 1. So I'm just going to think of these as infinite degree polynomial. Another advantage of thinking of them as infinite degree polynomial is that I can just add, subtract, or multiply generating functions at my will. Okay, so I can do this without any anything to check. In certain cases, I can also divide. I'll come to that whenever there is a need for division of generating functions. But this is what the setup is for me. Okay. So I have mentioned already that you have something called the generating function. So what is the use of this generating function? Why do we need really generating functions if we just know what the numbers are? So if you look at the sequence of partition numbers, then I already told you that they grow very large very quickly. Without a generating function, it would become very difficult for us to understand how these numbers are growing, or if there is a connection between these numbers. So maybe it might be that every fourth number that appears, or every fifth number that appears in the sequence is divisible by 5, or every seventh number that appears for some arithmetic progression is divisible by 7. But we'd never know if we just keep on just looking at the numbers. We may be able to guess, we may be able to conjecture, but it will be difficult to prove without using techniques from generating function. Okay, so that's one thing. The other thing is that you can think of these as something like a clothesline. So you have this long clothesline where you are hanging all of these numbers. So first position you hang P0, second position P1, third position P2, and so on. And you can sort of pull along that line. And if suppose you want to focus on terms of the form, let's say P5n plus 4, then you keep on pulling. Whenever you see n equal to 0 will give us P4. You stop at P4, look at that, then again you pull, you go to P9, you look at that, and so on. So it gives you sort of like a mechanism to look at certain arithmetic progressions or certain things. It also becomes easy to prove combinatorial results by manipulating generating functions. Okay, I'll not go into too much detail about this, but if anyone is interested, then there is a very nice book which is called Generating Functionology. And it's a free book. It's by Wilf. So you'll get it online. So it has 5 chapters. The first chapter explains generating functions with some examples. Then the second chapter explains the properties of generating functions. And then the third and fourth chapter focuses on really certain nice combinatorial techniques. It's a very nice book. I recommend very highly. And the fifth chapter deals with analytic properties of generating functions. So you can think of these as complex series. Then you get certain nice properties of the generating function. Okay, so let's start now properly with our study of partitions and our study of Rogers-Ramanujan identities. Okay, and for that we are going to use mostly we are going to use generating functions, but sometimes we'll also use certain combinatorials. So I've already mentioned this, but this is the book that we are going to follow. It's called An Invitation to Rogers-Ramanujan Identities. It is written by Andrew Sills. It's published in 2018, I think. Let me just check. Yes, it's published in 2018. And there are about 6 chapters. We hope to do 4 chapters. Okay. So today we are going to start with some content of the first chapter. So I hope everything so far is okay, but we are going to move a bit faster from now on. So this was just preliminary thing. So I wanted to take some time to get you familiar with certain things. Okay. So the first thing that we want to figure out is there a nice closed expression for the generating function for partitions? And the answer is yes. It was already found by Euler, who gave the following result. So if you look at the generating function for partitions, then there is a nice representation for that. And this is just 1 over 1 minus q to the I, where I starts from 1 to infinity. Okay. So this is the generating function for partitions. Now, how do we know? Is there a way that we can see this? And I'm going to give you a sketch proof of this. I don't want to do the full details, but the sketch proof goes something like this. So if you look at just the first two products which appear here, okay. So the first 2 factors which appear is 1 over 1 minus q and 1 over 1 minus q square. Then we are going to use the geometric series expansion. So we know that 1 over 1 minus q is just 1 plus q square and so on. Okay. And we also know that 1 over 1 minus q square is just 1 plus q square plus q to the 4 plus q to the 6 and so on, right? So already we know this. But if we multiply these 2 out, then we can see something nice happening. So which is the following. So 1 plus, so I'm going to write q to the 1 here. Then I'll club together the terms where cube appear, okay, sorry, where q square appears. So 1 q square is coming from this when it is multiplied with 1 here. So I put a q square. Another q square is coming when this q is going to be multiplied with, sorry, it's not true. So not this q square, yeah. So it's going to be this q square, which is multiplied with a q here. So I'm going to write it as q1 plus 1, okay. And again, a q cube will appear when this q is multiplied with q square. So I'll write it as, let's put it as q2 plus 1. And another q cube will appear when I multiply q square with the q. So I get 1 plus 1 plus 1 and so on, okay. So if you notice what is happening in the exponents. So if you look at the exponents, you see, so the exponent for this one is q to the 0. So if you just focus on the exponents, you get a 0, you get 1, you get 2 and 1 plus 1, then you get 2 plus 1 and 1 plus 1 plus 1 and so on, okay. So all of these are actually partitions, but they are very special type of partition. So these are partitions of 2 where the parts are coming from just 1 and 2, okay. Again, these are partitions of 3 where the parts are coming from just the numbers 2 and 1. And similarly, whatever will be here will be a partition of 4 with parts coming from 2 and 1. Okay. So if you sort of multiply one more factor here, say 1 over 1 minus q cube, then you will see partitions where parts are coming from 1, 2, and 3. Okay. And you can keep on doing this. So if you multiply the next factor, which is 1 over 1 minus q to the 4, then you can see partitions appearing where parts are coming from 1, 2, 3, and 4. Okay. And if you keep on doing this, eventually you will exhaust all partitions, right? So because of that, the generating function for partitions is given by 1 over 1 minus q to the I. And you take the infinite product from I equal to 1 to infinity. Okay. So, I mean, this was probably a bit quick for some of you, but if you want, there is a nice explanation in the book. So I encourage you to look at it. Immediately we can get a result of Euler if we think along these lines. Okay. So another result of Euler is this famous result, which says that the number of partitions of n into odd parts is equal to the number of partitions of n into distinct parts. And now if you think about what we did in the previous steps, then the generating function for all partitions was generated by these factors 1 over 1 minus q, 1 over 1 minus q square, 1 over 1 minus q cube, and so on. But now if you restrict that parts of size 2, 4, 6, 8, basically all the even numbers, if they cannot appear, then we don't need to multiply the factors 1 over 1 minus q square, 1 over 1 minus q to the 4, 1 over 1 minus q to the 6, and so on. So that means the generating function for partitions of this type, that means the partitions where only odd parts appear, the generating function would be just 1 over 1 minus q to the 2i minus 1, where I is going from 1 to infinity. So that means we are just taking the factors where the exponent of q is odd. So the first factor here is 1 over 1 minus q. The second factor here is 1 over 1 minus q cube, and so on. Okay. So this would be the generating function for partitions into odd parts. Now, what about partitions into distinct parts? Okay. So if you think again, you see that in any partition, if you have that the parts are distinct, then there are only two possibilities for each part. So if you look at, say, some partition of 20 and you are considering if the part 5 is there or not. Okay. So the two possibilities are just 0 and 1 binary. So either the part 5 is there or the part 5 is not there. So that is going to be generated by either 1, which is saying that the part is not there, q to the 5 is not there, or q to the 5, which says that the part 5 is there. Okay. So what I'm trying to say is that the generating function for this is 1 plus q to the I, where I is going from 1 to infinity. Okay. So the generating function for partitions into distinct parts is given by this. Each time we look at the part 1 and we decide whether the part is there or not there. Second part 2, whether the part is there or not there, and so on. Okay. So two choices. 1 is signifying that it's not there, and q to the I is signifying that the part q is there. And what the result is saying is that both of these things, these two things, are equal. Okay, so the generating functions are equal. But why is it saying that the generating functions are equal? So what I'm using here is the following. So to show that some sequence an and another sequence bn is equal, so that means they are equal part by part, okay, term by term, it is enough to show that the generating function for the sequence an is equal to the generating function for the sequence bn. Okay, so this is what I am using in the previous argument. So if I'm able to show that these two generating functions are equal, then this result would follow. Okay, and this will be an exercise that I leave it to you, because we can just, if you look here, we can just multiply something on the top and something on the bottom to complete. So it's like the formula a square minus b square is equal to a plus b into a minus b. We just look at what the factor a plus b can be, and then we see how we can argue from there. Okay, so this is going to be a homework, so I don't want to do it. It's just 2 steps from there. Okay, and there is a nice combinatorial proof also. Again, I'm not going to do this. Sorry, combinatorial proof. If you're interested, this is called Glacier's bisection. Actually, Glacier has given a more general result, but so that's for some other time. It's not for today. Okay. All right. So this, the introduction to partitions is almost done, and this leads us very nicely to an example of a baby Rogers-Ramanujan identity, if you will. So remember when I showed you the Rogers-Ramanujan identity, the left hand side was a sum, and the right hand side was a product. And I said that there are other identities of similar type. There is actually an easy identity of that type, which we can actually prove right now. So let me first state the identity, and then we'll see the proof. Okay. So I mean, I'll just write it as a theorem, but it's a very easy identity. So it looks almost like the Rogers-Ramanujan identity. Okay. So instead of, so if you remember Rogers-Ramanujan identity on the left hand side, in the numerator you had q to the n square and q to the n square plus n, but this time we'll have a q to the n only. Okay, and the bottom is same, 1 minus q, 1 minus q square, and so on up to 1 minus q to the n. So n going from 0 to infinity. This is the left hand side, a sum, infinite sum, and then the right hand side is going to be an infinite product, and this time the product is just the generating function for partitions. Okay, so this is just the right hand side is just the generating function for partitions. So we want to also see in some way that this is also another expression for the generating function for partitions. And as I mentioned, the proof is not difficult. So this is an example of a proto-Rogers-Ramanujan type identity. So let's look at how we can maybe prove what it is. Okay, so if you recall the result that we proved using conjugation, so that talked about partitions where the largest part was of a fixed size, and it gave you another partition where the number of parts was of a fixed size, okay, fixed number. But this time we are not going to say exactly that the largest part is, say, m. We are going to say that the largest part is at most n. Okay? So the result is the following. So our aim is to prove this one, and we are going to see a proof now. So the result that I want to use is the following. So the number of partitions of n where the largest part is at most m equals the number of partitions of n where the number of part is at most n, where the number of parts is at most m. And if you think about this, actually the proof is exactly the same. So what we did was, so a partition where the largest part is at most m means that the first row in the Ferrar's diagram will have at most m dots. So that means the number of dots will be less than equal to m. And if you take the conjugate of this, if you do that conjugation operation, then this is transformed, the first row is transformed into a first column, where again the number of dots is less than equal to m. That means the number of parts in the corresponding partition that you get is at most m. So this is just the same proof, but with just some, maybe changing one or two words there. Okay. So this result I don't need to prove really, but what I want to see now is what is the generating function for this. Okay. So if you think about this, the generating function for this part, so let me underline this. Partitions of n where the number of part is at most m. So the generating function is given by this. So 1 over, let me, so 1 over 1 minus, sorry, I made a mistake. I should have marked the other part because, yeah. So let me write down the generating function and we'll see what that is generating. So now if you look at what I have written, this is the first m factors of the generating function for the partition, okay, for the integer partitions. So the generating function for integer partitions was this infinite product, but I just took the first m products out of this. So which just says that all my partitions are being generated by parts of size 1, 2, 3 up to m, okay. So that means this is the generating function for partitions of n where the largest part is at most m. Okay? If I have a part which is greater than m, then this is not going to generate this. Whatever I have written down is not going to generate such a partition. Okay. So this is the generating function for 10. Okay. And let me denote by say PL of n. This is going to be the number of partitions where the largest part is at most L. Okay. This is again equal to the number of partitions where the number of parts is at most L. This is already what the theorem says here. Okay. And let's see what PL of n minus PL minus 1 of n is. So if you think about this, so PL of n is counting the number of partitions where the number of parts is at most L. That means it is including partitions where the number of part is L, as well as it is including partitions where the number of part is less than L. Okay. And similarly, PL minus 1 of n is including partitions where the number of parts is at most L minus 1, but it is excluding all the partitions where the parts, where the number of part is L. So if you subtract these two quantities, what you get is that this gives us the number of partitions with exactly L parts. Exactly L parts. Okay. So now I'm going to write a generating function for this. So let's denote this by, let me use say QL of n. Okay. So this quantity. So I want to know what is QL of n. So Q is a bad notation. Let me change it to say BL of n. Okay. So I want to know what is this generating function. I can write BL of n. I can just replace it by PL of n q to the n minus PL minus 1 of n q to the n. But I already know what is the generating function for this. So it's exactly this with m replaced by L. I also know what is the generating function for this. Again, this is exactly this with m replaced by L minus 1. So I put those things here. Let me just do it in one line. So I'll just have 1 minus q square, and so on up to 1 minus q to the L. So this factor, the denominator, will appear in the first generating function. Okay. So I have a 1 here. But one factor is not appearing in the second generating function. So basically 1 minus q to the L is not going to appear in the second generating function. So I need to subtract 1 minus q to the L here. And if I do this, then the 1 will get cancelled. So I'll just have q to the L in the top. Now think about uh, another scenario. Okay, so BL of n is counting the number of partitions with exactly L parts. So if I add B1 of n, B2 of n, B3 of n, and so on, then I'm basically counting partitions with exactly one part, plus partitions with exactly two parts, plus partitions with exactly three parts, plus partitions with exactly four parts, and so on. All these partitions are of n. Okay. So what I'm saying is the following. So Pn is actually just summing over all of these Bn's, L from 1 to infinity. Okay. So you can also include the 0 because it's not going to make any change. We are just going to add a 0. Okay. So, I mean, this should be clear because BL is counting the number of partitions with exactly L parts. So a partition can have exactly one part, it can have exactly two parts, and so on. So if I add all of these up, then I'm going to get all the partitions. Okay. So that means the generating function for Pn is nothing but taking this, right? But what is this? We already found that this is equal to, sorry, L from 0 to infinity, q to the L divided by 1 minus q up to 1 minus q to the L. And what is this? We already know that this is equal to this product. So if you go back to the result that we wanted to prove, then we see that the right hand side was exactly the generating function for partitions, which for some reason I have written it as a left hand side here, which is this. And if you again go up and you see that the left hand side is exactly what we have on the right hand side now. Okay, so exactly this. In that case, L was replaced by N. So basically, this was the proto-Rogers-Ramanujan identity that we had to prove, and this is a nice, combinatorial proof of what we did. Okay, so this identity is also an identity of Euler. And as a homework, let me mention another identity which is due to Jacobi, but I'm not going to give you the hint of what. So I have, it's similar to again Rogers-Ramanujan identities. Okay, so I have q raised to the L square. Again, L is going from 0 to infinity, but in the bottom, instead of 1 minus q, 1 minus q square, and so on up to 1 minus q to the L. If I just had this, I would have the left hand side of the first Rogers-Ramanujan identity. But what I have is actually square of this. Okay, so this is also equal to the generating function for partitions. So this is a homework. Okay, then I'm not going to do this, but it has a nice combinatorial way of looking at this side. So we can discuss this, later if someone wants to discuss it, but I'm not going to prove it. What I'm going to prove is what is called Euler's pentagonal number theorem, which is the next result of Euler. So you can see that there have been several results by Euler now. Already, I think 3 results by Euler we did. That is because Euler was, the first person to systematically start the study of partitions. Okay, it was, it's a quite old branch. And Euler gave several results. After that came people like Jacobi and so on. And even in the last century there was Ramanujan, Hardy, and now it's a very active field of research. Okay, so the next result is quite important because of that it has a name. It's called Euler's pentagonal number theorem. So what Euler did was he looked at the reciprocal of the generating function for partitions. Okay, so that means he took this product and he looked at the reciprocal of this product. So the reciprocal of this product is just product of 1 minus q to the I. Okay, so I 1 to infinity. And then he looked at the expansion for this, and he saw that there is a nice pattern in the terms that appear. And we gave this result. So I'm going to write down the sum side. So again, this is a product equal to sum type identity. So the product side is just the reciprocal of the genetic function for partitions. Now the sum side is this. So it may look very different from what we have been doing, but we'll see in some time why this is very natural. What is appearing there? Okay. So this time we have a infinite series which is going in both directions. -1 raised to the j, q raised to the j by 2, 3j minus 1. Okay. So this is called the Euler's pentagonal number theorem. Again, like several of the famous results in this area, there are several proofs of the Euler's pentagonal number theorem. Um, uh, Even now, like up to 2-3 years ago, there have been new proofs of Euler's pentagonal number theorem. So the most recent new proof that I know uses some tiling pictures, which is quite a nice proof actually. It proves a more general result by Sylvester, from which the result by Euler follows. Okay? But we are going to see a proof which is due to Franklin. It's a bijective proof, and it's a nice bijection. It's because of that, it also has a name. It's called the Franklin's bijection, and it's used in other results as well. Okay, but to go to Franklin's bijection, we need to recast whatever Euler has written into a more combinatorial way of looking at this result. Okay, and that was given by Legendre. But before that, let me give you the motivation of why Legendre came up with whatever he came up with. Okay. So if you observe, this left-hand side is almost the generating function for partitions into distinct parts. Okay. So if you recall from several slides back, the generating function for partitions into distinct parts was product 1 plus q to the I. Okay. But here we have 1 minus q to the I. It's almost the generating function for partitions into distinct parts. Okay. So let's see few terms. What are these terms? How do they look like? Okay. So let's see the LHS. So let me take out, two terms first, okay? 1 minus q and 1 minus q squared. And then I leave all of the other terms. So if I do the factorization, 1 minus q into 1 minus q squared, what I get is the following. So I have 1 minus q to the 1 minus q to the 2, but I have a plus q to the 2 plus 1, okay? So when I multiply this with this, I get a plus. And let me take out one more term now. So 1 minus q cube, 4 to infinity. And again, I do the product. So I open the brackets. So I have 1 minus q to the 1 minus q to the 2 plus q to the 2 plus 1. This remains same because I multiplied with the 1. And I'm going to now multiply it with minus q cube. So I get a minus q cube. I get a plus q3 plus 1. I get a plus q3 plus 2. And then I get a minus q3 plus 2 plus 1. And I have, so I'm not going to do one more step, okay, but because the pattern is now almost clear. So if you look at the prefactor that I got by multiplying the first 3 factors of this infinite product, you see that there is a bunch of terms which appears with a negative sign, and there are other terms which appear with a positive sign. But there is a distinguishing feature between these minus signs and plus signs, okay, and which actually is true. So if you look at the minus signs, it appears. So okay, first of all, let's also notice what the exponents give. The exponents are still generating partitions into distinct parts. Okay, so you see that this is a partition into distinct part, this is another, this is another. All of these are actually partitions into distinct parts. It's still generating partitions into distinct parts, but it is generating partitions into distinct parts, sometimes with negative sign and sometimes with positive sign. Where does the negative sign appear? So you see that the negative sign appears when the partition is 1, it's 2, 3. Then 3 plus 2 plus 1. Okay, so basically these terms, it appears with a negative sign, and the other terms, so partition 2 plus 1, 3 plus 1, 3 plus 2, these appear with a positive sign. Okay, Now, if you look at the number of parts, then you see a clear distinction between the two rows that I have written down. Okay. So in the first row, I see that the number of parts is always odd. Okay. Number of parts odd. And in the second row, I see that the number of parts is always even. And this is actually true. Okay. So if you do the expansion of the reciprocal of the generating function for partitions, you get whatever expression that you get, it's going to generate the existing parts, but the coefficient will be -1 when the number of parts is going to be odd, and the coefficient will be 1 when the number of parts is going to be even. Okay, so this brings me to Legendre's interpretation. So what he did was the following. So I'm going to denote by Q E of n to be the number of distinct parts partition of n with even number of parts, and similarly Q O of n is going to be the number of distinct parts partition of n with an odd number of parts. So what Legendre said is that if you take the difference, so Q E of n minus Q O of n, then this is going to be either +1, -1, or 0. Okay, and when it is +1 or -1, it's going to be plus or minus 1 when n is equal to something like this. So 3/2j square plus or minus half j. Okay, so if n is of this type, then the difference between all the partitions of distinct parts with even number of parts minus the distinct parts with odd number of parts is going to be plus or minus 1. N is going to be 0 everywhere else otherwise. Okay, so now you might ask, how does Euler's result follow from this? I said that Legendre gave a combinatorial interpretation of Euler's pentagonal number theorem. So what we can do is, actually, if you look at the generating function for the left hand side, okay, so then this was not a nice notation. I should have used something else, but anyway, let's see. So this is the generating function for whatever I have mentioned in the left hand side. Okay, and the right hand side just says that this generating function is going to be equal to, so it's only going to be non-zero if your n is of this type. Okay, so and it's going to have a coefficient of -1 raised to the power j, q raised to the power 3/2 j squared plus or minus half j. Okay, and j is going from 0 to infinity. But now this is almost the right hand side of the Euler's pentagonal number theorem. So if you look at the pentagonal number theorem, the coefficient matches. This one also matches, but for the plus minus. But you see, the summation here was going from -infinity to infinity, but the summation here is going from 0 to infinity. So if we just replace j by -j, then we can extend this sum from -infinity to infinity. So -infinity to 0 would be one side, which would be 3/2 j square minus half j. And the other part, which is from j equal to 0 to infinity, would be 3/2 j plus half j. Okay. So this is actually the right hand side of Euler's pentagonal number theorem. What about the left hand side? Is this giving us the left hand side of Euler's pentagonal number theorem? And it is immediately clear from what we saw in this expansion. Okay. So this expansion is exactly what I have described as the left hand side of Legendre's result, right? So Euler's pentagonal number theorem will actually follow if we are able to prove the result by Legendre here. And I said that I'm going to use a bijection due to Franklin. By the way, it's interesting because Franklin's bijection. So we now know that United States is one of the world leaders in mathematics at this point of time, but it was not always so. The world center of maths was in Europe. And Franklin's result is from the late 1890s. He was a student of J.J. Sylvester, and it's sometimes considered that Franklin's result was one of the first major results in mathematics that came out of United States. Okay, so anyway, so we are going to use a bijection of Franklin, and I'm just again going to draw some pictures, and I'm going to tell you what that bijection is. Okay, so we're going to define a map on partitions into distinct parts. Okay, so let's pick a partition into distinct parts. So I'm going to pick a small one. Okay, so let's say 6 plus 5 plus 3. So this is my partition into distinct parts. Now Franklin's map is the following. So the forward side of the map says that you look at the longest diagonal that you can draw, unbroken diagonal that you can draw from the rightmost tip. Okay, so that means look at this diagonal, the longest diagonal that you can draw with the dots from the right tip. So, but we cannot move further because there is no dot below. So the diagonal will stop here. Okay, and we apply whatever this map F for Franklin. So Franklin's map, when we apply, we move these dots that we have picked in the diagonal to the bottom. So I'll be left with 5 dots in the first row, 4 dots in the second row, 3 dots in the third row, and then I'll move the 2 dots that I picked and I'll put it below. Okay, so I'll put it in the last row basically. So this is the forward side of the map, and the reverse side is clear, right? So you pick the smallest part and then you flip it and make it as this contiguous diagonal. So now if you think about this map will work. So 2 things to notice about this map. Okay, so the first thing to notice is that whenever we apply this map, we end up with another distinct parts partition. But not only that, we end up with a distinct parts partition where the number of parts is 1 more than the number of parts that we started out with. So that means if the number of parts here is odd, then the resulting partition will have even number of parts. And if the number of parts here was even, then the resulting partition after applying Franklin's map would be odd. Okay, so I think I've stuck. No, it's working now. All right, so that's the first thing to notice. Okay, so that actually gives us almost gives us what this difference would be. So if everything works out well, then you are always matched with this even number of parts and odd number of parts. But there is a problem. This map does not work for very specific kinds of partition. So think about this. If you had, in this previous case, if you started with, 6 plus 5 plus 4, okay, suppose this was your distinct parts partition. It's still a distinct parts partition. We can still form this longest continuous diagonal, okay, and we can still apply, at least we can try to apply Franklin's map. So if we apply Franklin's map, we get this partition. But now there is a problem. The partition that we get here is no longer a distinct parts partition. We see that 2 parts of the same size appears here. Okay, so that means Franklin's map will not work for very specific type of partitions where the diagonal that you draw interferes with the last row. Okay, so if the last row and the diagonal that you are drawing has a common intersection, then Franklin's map is not going to give you a distinct parts partition. So this is the first problem. And the second problem is again similar. So if you have something like, say, 5, 4 and 3. Okay, so again this is a distinct parts partition, 5, 4, 3. Again we can draw this diagonal, but now if we apply Franklin's Franklin's map, then we get a partition, then we get a diagram which is problematic. So this is the last row, but this is now no longer a partition. It's not a valid partition because the parts have to be non-increasing. So when you go from the top to bottom, the first row has to be as long as the second row has to be as long as the third row, and so on. But in this case, the last 2 rows, they don't match. The penultimate row is not as long as the last row. So that means whenever you have a partition of this type or a partition of this type, then Franklin's bijection won't work. And if you think about this, these two type of partitions are very special. So in the first type, the number of dots in the diagonal that you drew was one less than the number of dots in the smallest part. So in this case, the number of dots in diagonal was equal to the smallest part minus 1. Okay? And in the next case, in this case, the number of dots in the diagonal was equal to exactly the smallest part. So these are the two problematic cases for Franklin's map. Okay, so that means in this case we cannot apply Franklin's map and will be actually somewhere landing up here, okay, which was the first case of Legendre's result. Okay, and I'll let you do it. So what we have drawn for the problematic cases are exactly, you know, what are called pentagonal numbers. Okay, so the partitions that we have drawn here, these are special type. So they are actually partitions of pentagonal numbers. And again, I'll leave it as a homework exercise to fill in the gaps. Okay. Right. So this was a bit more involved, this map, than the previous map. And I mean, so combinatorial thinking is helpful, but it does not guarantee that it will be nice every time or it will be easy every time. In this case, it is nice, but it is probably not very easy to come up with. Sometimes it will be easy to come up with, but it might be very messy. Okay? So let's move on to the final result that I want to touch today, okay? And then we'll stop for today. And this is actually a corollary of Euler's result. So the corollary says that for all n greater than equal to 0, actually 0 is not included. So for all n greater than 0, we have P of n, which is the number of partitions of n, is actually given by a recurrence. You can write P of n in terms of smaller values of n, okay? Smaller values of P of n. So P of n plus 1, n minus 1 plus P of n minus 2 minus P of n minus 5 minus P of n minus 7 and so on, okay? And the proof is quite easy. So just multiply these two things. So 1 over q to the I, which is the generating function for partitions, times the left hand side of Euler's pentagonal number theorem, which was, sorry, the right hand side of Euler's, so no, left hand side of Euler's pentagonal number theorem, which is just the reciprocal of the generating function for partitions. And this is clearly equal to 1, everything cancels out. But I can recast this as summation p and qn, and going from 0 to infinity. I can recast this as summation j from minus infinity to infinity minus 1 to the j, q to the j, 3j minus 1 over 2 equal to 1. So now this is clearly going to be a series in q. Okay, it's going to be some power series. If you expand this, it will be some power series. But the right hand side is not a power series, it's just a constant one. So that means everything disappears except whatever is the coefficient of q to the 0. Okay, so that means the coefficient of q to the 1 is 0, the coefficient of q to the 2 is 0, and so on. So in this case, so just use now Cauchy product. So if you don't know, I would advise you to look at what is Cauchy product of power series. So there is a way to write down the product of this, and we compare term by term. If we compare term by term, we'll get the recurrence that we just showed. So this recurrence can be used to actually find the value of P of n for very high numbers. And some of the computer algebra system, I think, still uses this recurrence to calculate the value of the number of partitions. Okay. So let me stop here today because I think we covered a lot of things related to partition. The next thing that I want to go into is some identities, which we can prove using a technique called the WZ method. So, but I'll do it next time. So if you have any questions, then please feel free to ask.
Okay, Professor, can you discuss the odd even? I mean, how you told this is odd and how you told this is even. So,
This map,
I, no, 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 please.
this one.
Yes, yes.
Okay.
Oh, yes, parts odd, parts even.
Sure. So the goal was to prove this result, okay, Euler's pentagonal number theorem. So we just focused on the left hand side uh, first. So for the left hand side, I just picked the first two factors. I took it out and I kept everything else inside, okay, inside the product. So when I expanded the first two products, then I got something like this. I did one more expansion with 1 minus q cube, and I can do one more, but I did not do it because it would be too long. But after this expansion, we see that there will be some terms with a minus sign and there will be some terms with a plus sign. And if you look at the exponents, then you see that the exponents are actually partitions into distinct parts. So you can see 3 plus 1, 3 plus 2, 3 plus 2 plus 1. So all of these are partitions into distinct parts. And if you expand further, you will get more and more parts. Okay. So for example, 2 plus 1 will appear in the next iteration. 3 plus 1 will also appear in the next iteration, and so on. Okay. So, but if you list all of these exponents and if you look at the signs that these exponents are associated with, you will see that exactly when the number of parts in those exponents is odd, then the sign is negative. And whenever the number of parts is even, the sign is positive. So that is what I wanted to actually focus on here, which is which suggests that we look at the difference QEN minus QON, which is giving us the difference between such partitions, distinct parts partition of n with even number of parts minus distinct parts partition of n with odd number of parts. Okay.
Okay, Professor. Hello?
Yes.
Okay, Professor.
Okay. All right. Okay. Any more questions? Let me stop.